So I'm John Bent. I've been thinking for a long time, right? Many years in HPC storage, thinking about lots of different things, and in particular, thinking about how to deliver, how to integrate NVMe into data centers. And NVMe is this really, really wonderful media of fantastic potential to improve the performance for your workflows, your applications, to deliver more insights in less time. But it's got all sorts of complexities, all sorts of idiosyncrasies. You can't just think of it like a faster hard drive. You've got to do garbage collection, write endurance, all of these weird things. Plus, you don't just replace hard drives with it. Instead, you integrate it into your workflows. And so I don't expect people to sort of look at these, but it's just to show that in order to really deliver the potential, to get the potential benefits of the SSDs, of the NVMe into your workflows, requires innovation. And as I've been in the industry looking around, it's DDN that has really been the most successful in delivering innovations into products. All sorts of very cool innovations are happening. Pattern-aware prefetching, write anywhere layouts, embedded, software defined, and it's the full stack. It's all the way from client, through the NVMe, through the disk layer as well, all the way to cloud, from acceleration all the way to object. And just to give you a hint of some of the complexities, everyone knows, okay, now we need to have data centers with both NVMe and with the spinning drives. But you can't just add them to your data center and expect that suddenly things are going to go faster. And the first hard thing to do is to take a whole bunch of devices and turn them into a useful block system. All sorts of complexities and challenges. There's write holes. You have to deal with failure during rebuild. You have to hide the fact that a bunch of devices have been virtualized into a single device. You have to worry about transactions in order to protect resilience, read after write, hiding latency, what happens when some drives are slow. DDN has been very successful here. We've got our flagship product, the SFA-OS, offers enterprise reliability. It's very flexible, very portable. And it does that with a whole bunch of very cool innovations. And again, I'm not going to talk necessarily about everything here. You know, it's got partial rebuild, data protect react, SFX cache. But please, we'll be here all week. We're at the booth. Anything that you're interested, come. You can learn more details about all of these innovations. But to suffice it to say that it turns a bunch of devices, be the NVMe or be the spinning hard drives, into a useful block layer. But you're not done. So now you've got block. But it's got to become file in order to be useful to applications and workflows and improve time to insight. And not only does it have to be file, but it has to be distributed file. And it has to be distributed file that's accessible via parallelized streams so that you can extract all of the benefit of each individual device across the distributed system. And what's challenging there, you got to worry about consistency, availability, consensus. Split brain syndrome is very complicated. Failover, resilience, all while maintaining this performance so that you have faster time to insight because you have extracted the full potential benefits of NVMe. And how do we do this? We've got some more flagship projects. We have Exascaler, it's the world's #1 file system. We also have Gridscaler, which is the world's other #1 file system. And I don't want to get into this, but it was mentioned earlier today that the reason, Robert discussed this, there's no necessarily one single file system which is best for every application. And so now that we have IME, which is yet another very powerful file system interface for your applications, for your workflows, for acceleration. But now that we have these distributed file solutions, we're still not done. We have to deliver them as a solution to our customers who want to be able to think about their science and not think about their storage and just have it work. And what's challenging there, you want to get balanced hardware. So you have, economically efficient solutions. You're not getting more than what you need, and you're extracting the performance from what you do get. You have to match the software to the workflows. It has to be usable, manageable, serviceable. And DDN knows exactly how to do this. We have a fantastic professional services organization, and we do really deep integration into your workflows. I'll talk a little bit more about how we do that in a second. Global support and expertise. The other thing that DDN has realized is that these NVMe devices are fantastic, but there's not one single fit solution. And so we've been able very successfully to integrate our NVMe devices across our product line. We have the IME 140 for the really toughest IOs. We have the SFA 200 NV, the SFA 400 NV. Please, again, for more details, come to our booth. That's the whole solution. Those are the all NVMe arrays. Plus, we have our 7990s, our SFA 14Ks that James was talking about, where you have scalable performance and capacity. You get the blend that you need from those hybrid solutions. And what do you get? How are we able to extract the potential of flash and deliver it to your workflows? With the NVMe acceleration in the IME 140, 20 gigabytes per second in one use is something that Paul talked about at the beginning today. The SFA line of those NVMe arrays, 20 to 40 gigabytes per second in 2U. Full file system completely embedded. With the SFA 7990, the 14K, 20 to 60 gigabytes per second in 4U, plus 21 petabytes per system. And guess what? If you need more than 21 petabytes, it's no problem. We add systems. We get linear scale out and linear scale up as you add systems. So, how then, right? You look at that product line, and it's almost, but it's not, it's almost too much of a good thing. And how do you as customers know which of those product lines is the most appropriate for your workflows, that's going to accelerate your time to insight and economic efficiencies the best? So here's an example of an oil and gas customer that was running reservoir simulations and discovering that they had some performance slowdowns. What we did is we went into their work center and we profiled their application. We sat there and we looked at their application, we looked at their network. Case earlier said, hey, we've got great storage, we've got great GPUs, the network is the problem. And when we come in and we integrate workflows, we integrate storage with your workflows, the first thing we do is we check the network. Is the network the problem? And in this case, the network wasn't the problem. We profiled the application. We said, you know what? The problem is that your storage is not fast enough. You've got very difficult, challenging I/O problems and patterns, and IME is the solution. We implemented it, and we solved their problem. We got them a 4x speed up. Okay. So just a little bit of more about why is it challenging to use NVMe. And the problem is with traditional file systems, the NVMe is hidden next to the hard drives within the file system. And what we're seeing is that modern workflow I/O patterns are increasingly chaotic. You know, when HPC was brand new, there was 5 applications, and they had scientists that were willing to spend a lot of time thinking about storage and optimizing and using the storage system in the way that's easiest for the storage system. What we're seeing now is that there's an explosion of applications that are running. More and more people want to co-locate multiple users, the multi-tenancy that we just heard about in the last talk, onto one single system. So first of all, there's lots of applications that don't want to think about I/O, and that do I/O patterns that are problematic for traditional systems. Plus, even the applications that behave well according to traditional file system parameters are rendered random when they're run concurrently with other applications. And as they go through the thick file system layer, it restricts performance even though you've got these fantastic, wonderful, potential-rich NVMe devices inside your storage system. So what does IME do? IME does a reorganization transparently. Applications don't know, but transparently IME reorganizes the data flow so that you get more IOPS, more gigabytes per second between your applications, between your workflows and IME. And then IME, again, transparently, in the background, hidden from your applications, will aggregate all of the data through a simpler interface, move it down to the file system, and now the file system is freed from the burden of trying to simultaneously provide IOPS and bandwidth and capacity. And the underlying file system says, thank you very much, IME, for doing my IOPS and my bandwidth. Now I'm going to focus on capacity. So just a little bit more about what IME is, and then we're going to talk about how IME does it. IME accelerates your applications, your workflows, your IOPS by up to 100x. Reduces power usage by 50%, improves data center density overall by 67%. It extends flash life a lot. It's very adaptive. We talked about the problems with thick file systems. IME is a very thin layer. It gets out of the way. It does write anywhere. It's scale out. Distributed declustered parity that comes from the client. I'll talk about that on the next slide. It's software defined. It's able to utilize commodity hardware. As we said, it gets rid of those file system bottlenecks. So first of all, how does IME accomplish a lot of these things? It's got flexible, scalable client-side erasure. One of the complexities with client-side erasure is that you might do read, modify, write over the network. That's horrible. And in that situation, case becomes 100% correct. The network is a huge problem. IME avoids that problem. It doesn't do read, modify, write. It does flexible striping and erasure regardless of what the pattern is, using its write anywhere layout. And then because we're doing client-side erasure, we can leverage single-ported commodity SSDs and drive the costs way down. The deep storage, as we said, is capacity optimized because IME reorganizes it. It uses RDMA. Again, it makes sure that whatever the network is, it extracts the efficiencies from the network by doing RDMA on both reads and writes. It has a lockless network protocol. That's very important. That's one of the things that the thick file system imposes on your workflows and restricts your performance. IME IOPS scale infinitely because you don't need coordination, you don't need to pass locks. There's zero penalty for file sharing. Yeah. So here's an example. I want to talk about WRF. And earlier it was talked about that supercomputers are all about changing compute-bound problems into I/O-bound problems. And that's actually the worst thing possible because supercomputers are all about enabling computation. The CPUs are the most precious resource in the machine. And so what is DDN about? DDN is 100% dedicated and focused to turning data at scale problems and returning the bound to the compute. DDN takes I/O-bound problems, turns them back into compute-bound problems, and that's where your workflows need to be. That's the fastest resource in the system. You want to run at the CPU speed. WRF is a weather simulation benchmark that was bounded by I/O. It was an I/O-bound problem without the IME. We put IME on it, and suddenly it's compute-bound again. We reduced the I/O time by 17x, which improved the overall wall time, the overall time to insight, by 3.5. We converted from I/O-bound back to compute-bound. I want to talk about 3 customers that have been really happy with IME. One of them is a small customer. They're a startup in San Francisco that's doing this very cool retail problem. What they're doing is they're doing sensors in the retail stores to make shopping a more convenient experience for all of us. Cameras do real-time inference as customers pull products off shelves. They say, oh, that's ketchup. The ketchup went into the basket. Oh, that's toothpaste. The toothpaste went back onto the shelf. They chose another toothpaste that's in the basket. The camera knows who you are. When you leave the store, you don't have to check out. It's all automated. The system knows who you are. And this company is a very small company. Very, very smart people. They know how to do AI. They know how to do vision. They know how to do image detection and inference. But they don't know storage, nor should they. But all of a sudden, they realized that in their systems, everything was going too slowly. And they identified that it was a storage problem. And they came to us and they said, please help us. We don't understand storage. And tell us what we need to do. So we came, just like we did for the oil and gas company, we profiled their needs. And we said, okay, we know exactly what your problem is. You're using NFS. You've got these locks. You don't get parallel performance from your hardware. And what you need is this tool called IME. It's this fantastic appliance, and it's a blend of NVMe and hard drives. And they said, oh, no. That sounds too complex. Just give us all flash. And we said no, or we didn't say no. We said, actually what we would like to do is we would like to give you a more economic, efficient solution. And the fact is that IME blends those such that you don't realize that it's there. And you're a small company. We want you to be successful. We want to grow with you. So let us give you what's economically most efficient for you today. Use the savings to hire more engineers to speed up your computation, and we will grow with you. As you need more, you're going to be a growth company, right? Really, really fantastic company. Let us give you only what you need now, and we will grow with you in the future with incremental growth. Slightly bigger customer, EPFL, is doing the Human Brain Project, and we're really excited to work with these customers. They're doing fantastic things that are making all of our lives better, right? What's more important than brain health, okay? They do neuroscience, medicine, and computing, And again, they had I/O bounds, and we wanted to convert them back into compute bounds. They're medium-sized customers. They got 4 IME nodes, and all of a sudden, we got them 1,000x speed up when they scaled to 84 nodes with their NeuroMap application. Did I miss one? One of our larger customers, JCA-HPC. They're a research university, which means that they run lots and lots of different applications. They have quantum chromodynamics, they do electron dynamics, a lot of simulation of atmosphere and ocean and earthquakes, optical material science simulations. And what's challenging when you're a research university is that there's lots of applications that A, are running concurrently and interfering with each other, and B, are run by scientists who want to think about their science and not become storage experts. And there's not enough time in the day to tune all of those different applications for storage. We put IME in there. IME means you don't need to worry about if you're doing whatever patterns of I/O, whatever concurrency is being imposed upon you by the job scheduler. The system just works well. And this system works well enough that the IME system at JCA-HPC is the #1 system on the IO 500 list. By far, it's 50% better than the second solution. So those 3 customers actually illustrate that IME is the easiest way to deploy anywhere from gigabytes per second up to terabytes per second. You can have a small system, like what you have a small system with 1 node that can deliver in just 1.25 random write IOPS, 0.6 random read IOPS. Or with a medium-sized installation, like 4 nodes, it just scales up. And you can go all the way to 50 nodes. You can go higher than 50 nodes. 50 is what they have at JCA-HPC. More than a terabyte per second of bandwidth, more than 100 million random IOs. One thing I'd like to point out about these random IOPS numbers is sometimes you'll see other people cite their random IOPS, and they'll have high numbers as well. But typically what most people do when they report their IOPS, and you should look and ask, is they report the IOPS when they run a benchmark directly on the block device. Our IOPS numbers are going through a distributed file system interface. They're traversing the network in between. So we're able to get these IOPS with a file system across a network, going through clients and servers. So IME maximizes your Nvme potential, delivers the potential to your workflows in multiple ways. It maximizes the lifetime of Nvme. It maximizes the performance and the efficiency. With this graph, I think we're a little low on time. We have the panel. It's okay? Okay. So I want to talk a little bit then about how does IME maximize your Nvme lifetime. We talked before about how the Nvme devices are fantastic, wonderful devices full of all sorts of potential, but complex. They have idiosyncrasies. One of the idiosyncrasies is that they have endurance limits. They wear out quickly, which is disappointing because they can be an expensive resource as part of your data center solution. So this picture, that very top rectangle, shows the logical view of the blocks inside an Nvme device. The gray on the left is valid sectors that are holding user data. On the right is free unused blocks. The second rectangle down with all of the little red bricks going into it shows what happens when applications issue random writes. And what happens differently in parallel file systems and IME is how exactly those systems write those random bytes into the Nvme device. What a parallel file system will do is it'll do write in place. It will overwrite. Now, the SSD itself is a log-structured device, so the new writes in both the parallel file system and in IME go into the free space on the SSD. But what's different is that IME uses this log-structured device itself with a log-structured pattern, so that there's no invalidation of existing blocks. Whereas parallel file systems, all of these have become invalidated blocks. And the challenge with invalidated blocks is that they require garbage collection. So what happens in the parallel file system, I did a little bit of an animation, is that it has to do garbage collection, it has to do write amplification. That hurts both your performance as well as the lifespan of your NVMe devices. Contrarily, IME just flushes that data down to the parallel file system. It informs the SSD that it's no longer using those blocks. There's no garbage collection. There's no write amplification. It improves both performance and lifetime. And we have data that proves this. So here's the data. This line right here is how long does it take to kill an SSD, an NVMe device, when you're doing 4K random IOPS. The vendors will tell you that a particular SSD device is 1 drive write per day, or 3 drive writes per day, or 5. We took a 1 drive write per day drive, and those warranties from the SSD vendors are for 5 years. So what does that mean? It means that if you overwrite the thing 5 times 365 times, that's when the vendors predict that that SSD will fail. And that's exactly what happened. The y-axis here is the number of reserve blocks in an SSD. And as blocks start failing in an SSD, it will remap the failed blocks to the reserved blocks. And when it runs completely out of reserve blocks, it fails. It hits the plateau of death. And what we saw with the 4K random IOPS, without using IME, the device failed really about when the vendor predicted it would fail. When we use IME, it goes and it goes and it goes, and it lasts 4 times longer than the vendor says it will last. So we're extracting a lot more potential from the NVMe devices, even than the vendors tell you you can get. Did I skip 2? IME also maximizes NVMe performance. One of the talks earlier said that 50% efficiency from Lustre was really, really good. What do you get with IME? With IME, we looked at the theoretical performance limits of the hardware on which IME was running. With IME, for sequential I/O, you get up to 93% efficiency from your hardware. IME also maximizes the flash usability. We talked a little bit earlier about the IO500 that was running at JCA-HPC. One of the things that the IO500 does is it forces vendors to not only report the hero numbers, but to also report the anti-hero numbers, to run a really, really challenging workload, and compare then the ratio of easy to hard. Because it's really disappointing for users that they don't know what their performance expectation should be from storage, because all they hear about is the hero number, which is completely unrealistic. So IME maximizes the flash usability. This graph here shows the degradation from easy to hard and compares IME to other flash systems. They all have massive degradation. They get about anywhere from 1/10 to 1/20th of their performance when they run with difficult patterns, which means that the users have no ability whatsoever to predict what their storage is going to see, and they have no ability whatsoever to get good performance, right? These computational scientists have to become storage scientists. With IME, they're blissfully ignorant of what's happening in the storage layer. Then one last thing, what I've been talking about is how NVMe is so wonderful, but challenging, and how DDN really allows you to extract the full potential of the NVMe and improve your time to insight. But there's one other thing about NVMe which is interesting, which is now that you have NVMe in your data center, you have to reimagine the role of hard drives. There's now opportunities, as we mentioned earlier, for hard drives to more aggressively optimize themselves for capacity. And DDN has solutions there as well. These are our 9012 drawers. It's 1 petabyte in 4U. You can do up to 20 petabytes served by just one DDN 14K controller. So we've got the performance optimized solutions, we have the capacity optimized solutions, and we provide an end-to-end solution. Transparent tiering all the way from client through NVMe, through our drive enclosures, to both on and off-premise cloud. And with that, I thank you very much for your time.